this last term on the right hand side, can we see some things getting clubbed together? For example, do I know is alpha grad fk minus xk anything that we already know? It's negative of yk plus 1, and so this term will simply become, what will it become? It will become x star minus yk plus 1, right? So this is good because I have now brought yk plus 1 into the picture. Bringing yk plus 1 into the picture is good because that will, what is the next step? Once I get yk plus 1, what is the next step from yk plus 1? Projection. So xk plus 1 will enter the picture. So I want xk and xk plus 1 both to enter the picture. I want this intermediate guy y to be gone, right? So that I don't have too many of these variables. So I've got yk plus 1 into the picture. So let's just rewrite this over here. So 1 by 2 alpha, okay. I have xk minus x star squared. I have yk plus 1 minus x star whole squared, okay. And this is a positive term, so this is going to be alpha grad fk squared by 2, right? Are we in a position now to telescope the series? Not yet. I still have my yk plus 1 sitting there, right? So let's look at this geometry over here. I have yk plus 1 and xk plus 1. So let's connect yk plus 1 and y star also, right? So I'm going to connect all the guys that are there in the expression. Okay, there we go. All of these guys are connected. So xk minus x star, this guy, is it here? It's this guy, right? And then I have yk plus 1 minus y star, that's let me use another color, that's here, that's here. Okay, so these two other guys over here. Okay. Now because yk plus 1 projects to xk plus 1, can we say something about the distance of y to x and xk to x? Will there be some kind of an inequality? Which will be closer to x star? Yk plus 1 or xk plus 1? Xk plus 1 because it's the projection, right? So we are assuming it's a convex set. Yeah, all of this is based on a convex set. So yk plus 1 minus x star, this distance, okay, is obviously greater than xk plus 1 minus x. That's clear from the geometry. Yeah. So I'm not writing convexity because it's true for, we wrote it at the beginning. So just one moment where you have to be a little bit careful. Yk plus 1 minus x star is greater than this. If I substitute this into the above expression, will the inequality remain the way it is? Yes, because there's a negative sign associated with it, right? So this can be, so let's substitute. So this will be fk minus f star 1 by 2 alpha. This term remains as it is, and this term will become xk plus 1 minus x star squared. So now you can see that, what I had in mind of telescoping will actually work now. I managed to eliminate y out of the picture, and I got, so it has the current iterate, it has the next iterate, and very nicely what they have opposite signs. One has a plus, the other has a minus. Okay. Is everyone clear at this point what we did? We have simply used this one property over here, that the projected point is closer to the solution point than the point which is farther off. And of course, this is only true for convex set. Okay. So now let's So I'll just write down a few terms. What will be the very first term left hand side? I had, look at your notes, first term would be for in terms of f, f0 minus f star, okay, less than equal to, first term will be x naught minus x star squared, then x1 minus x star whole squared plus what, alpha by 2 grad f0 squared, right? That's the first term. Everyone agree? 1 by 2 alpha. Okay. Now if I keep going like this, I am going to get finally fk minus f star, supposing I write it like this. This 1 by 2 alpha is there. What am I going to get? This is going to be xk minus x star squared minus xk plus 1 minus x star squared, right? And now if I, telescoping the series means to sum the left hand side and right hand side, okay. What am I left with on the what am I left with on the left hand side? Does anything cancel? No, right? Life's like that. These terms don't cancel. So I have a summation f of k, k going from 0 to, maybe I should not use k, f of I going from 0 to what? K, okay. And what else do I have? How many times has this guy come? K plus 1 times. Okay, so k plus 1 times f of star. What is left over here? 1 by 2 alpha. The first term and the last term. Those are the guys that don't cancel off. So I have x naught minus x star whole squared minus xk plus 1 minus x star whole squared. Does this other final term cancel? Negative, right? So this guy is going to be there as fine. Now this is the part where you have to get a little creative. So I have, if I have any negative terms on the right hand side, if I knock them off, will the inequality change? No, right? So I can as well write this as 1 by 2 alpha x naught minus x star squared plus alpha by 2 summation of grad fi, right? Because second term is, it does not affect the inequality, okay. So we are getting there. This term over here, I am going to pull out k plus 1 common from here, okay. K plus 1, if I take it common from here, what do I have? Okay, and I have f of x. Still not looking very good, right? I have this entire summation of function values on the left hand side. Now this is the time when we pull one more. See, there are only a few inequalities that are used. Can you name some inequalities that you know of? Cauchy-Schwarz is one, AMGM is one. There's another one which is called Jensen's inequality, right? So this is the time to pull the Jensen rabbit out of the hat. So if I look at Jensen's inequality and Jensen's inequality for a convex function. Does anyone know what it is? Okay. This actually you can appreciate from the figure. I'll write the inequality and then you can get it. In words, what is this saying? Function of the average point is below average of the function values. So when we drew this figure over here, yeah, this is assuming f is convex. I mean, it's the same as convexity. Yeah, right. So here you can see function. So function of average. So average point is, for example, over here, this green point over here, and the function value is here. This is below the average of the function values, which is the dashed line. The dashed line is f of x plus f of z divided by 2, right? So that is this pink point over here. So you can see this is, you can call it Jensen's inequality, or you can say this is basically the definition of a convex function, right? So let's scroll back over here. Okay. Yeah. Because that's the only term with, why did I pull out the term xk plus 1 minus x star? Because that's the only term with a negative sign. I want to simplify this expression as much as possible. It's a negative sign. So imagine, for example, this is, so imagine that the left hand side has a value of 3. Okay. This is say 5, and this is 1, and this is 0.5. Okay. So what is the left hand side? 3. What is the right hand side? 5 minus 1, 4. 4 plus half, 4.5. Now if I remove this term, the inequality still holds, right? So any negative term is not adding to it. So my goal is to simplify this expression as much. You can see, did it affect? I got rid of a minus 1. Did it affect the inequality? It did not affect the inequality. That's what I'm interested in. If it were an equality, I would not be able to do this. But it's not an equality, it's an inequality. So I have that freedom to play around with these terms. Did everyone follow? Right? It doesn't matter, right? I'm making a true mathematical statement, right? So we are almost there. We can substitute this Jensen's inequality. We are, the next step will show you what we are trying to get at. If I can get this scroll to work. So I'll write down the final expression after using Jensen's inequality, right? So f of, I'm going to replace average of functions by function of average. So this is going to be xk divided by k plus 1, okay, minus f star is less than or equal to x naught minus x star squared by 2 alpha plus alpha by, there was a k plus 1 outside, I'm going to move it to the right hand side, okay. So this is going to be k plus 1, 2k plus 1, and I have a summation of grad f I square, okay. So this is actually the final step of our not very, but somewhat complicated looking convergence proof, and now is where the sort of creative part is in interpreting what I have got. So let's interpret the result. What is the left hand side saying? What is the left hand side? So now we'll switch to plain English. What is the left hand side saying? There is an optimum function value which is given by f star. Everyone agrees? I have f of average of iterates. So what is it saying? The distance between f of average of iterates and the optimum function value, it's less than or equal to some expression. What is that some expression? There is a starting error, x naught minus x star, so it's like a constant. There's alpha, it's a constant. K plus 1, what is it telling me? As I increase my iterations, what is happening to this term? It's reducing. Let us say k tends to infinity. What will happen to this term? This term will tend to 0, right? If it tends to 0, what will happen to this guy on the left hand side? It will say that in the average sense, the average of the iterates is tending in function value to the optimum f value, okay. And this guy on the second term over here on the right, what about him? We have to make sure what? So there's a k plus 1 also in the denominator. So grad f should not blow up, it can grow, but it should not grow what? Faster than k. If it does not grow faster than k, if its growth is less than order k, what will happen to this term? This term will also die as k goes to large. So I'm adding smaller and smaller things. The net result is the right hand side is going to be some finite number which keeps decreasing, right? So this proof, it's relatively simple if you look at the other proofs in the literature, is saying that the average of the iterates is converging to the correct function value. Okay, so for that to happen, we'll just make a quick note of what we discussed. Grad fk, right, must not grow faster than order k. Must not grow faster than order k. Okay. And so this can be satisfied by things like Lipschitz, etc. Right? So this is not very hard to ensure. So what is this saying? That the average of the iterates this is what it is saying, right? Now what would have been really nice if instead we had f of xk minus f star less than equal to, or maybe something like this, right? This would have been great. Yeah. Okay, grad f square should not grow faster than k. Ideally, I would have liked this, that as my iterations go, f of xk and f star should come as close to each other as possible. This is what we would like. So this proof exists in the literature. It's much more complicated than what we did. So I'm not going to do it. What we've done is, that's why when I started the proof, I said we're going to do a slightly weaker version. The weaker version is we're going to prove that the average of the iterates converges, right? Average of the iterates in a long series of k, what you started out in the beginning is not so important, right? You may have 10 points that are far away, but as the operation goes on, you may come and converge close to the solution, right? So this is also true. This to be looked up. Okay. So the average of the iterates is not converging. I'm saying in the f value of the average of the iterates matches the optimum function value. Okay. You can imagine a downward, like a cup, right? The points are getting closer and closer and closer as you get to the optimum point over there, right? That's one way of looking at it. Okay, so this was you could say, the last proof of the course, which at least now when you say that you're using the projected gradient descent method, you know at least why it works. Otherwise, it's like downloading a algorithm from Wikipedia and implementing it without understanding why it works. So at least you have some idea of why it works. And you can see that in the proof, what are the key points? We have basically used properties of convex sets. Right? So there are courses where you study only convexity and convex functions for the entire semester, prove each of those properties very, very laboriously in detail. Right? So we have taken a little different approach. Let's just use those properties to build on and give you some interesting results. Okay. So I'm going to show you just one example of this projection operation. And in subsequent classes, we'll come up with a little bit more complicated examples. Okay, so the simplest example that you can think of is projection onto a feasible set, which is a ball. That's the first projection example that we're going to take. Okay, so the L2 ball, yeah. Yeah, projection is giving me that point in the feasible set closest to the point that I'm asking. So this is my feasible set. You can see that this is a sphere, right? It's a sphere in n dimensions, and I'm saying this is my feasible set. X must live inside this. Now, So let's just draw a two-dimensional version of it, and here is my point x naught. Okay, and what I want to work out is what is okay. This again looks simple enough that you could solve this problem without any calculus, without any Lagrangian business, right? So when, let's take two cases when x naught is in the feasible set, projection operation obviously is what? X naught. Okay. Now when x naught is not in this, what is the solution to this problem? It's very simple. Anyone? Smaller circle, okay, but can we draw this with a pencil and ruler? Correct origin, exactly. Take the origin, connect it over here, and the point over here, right? This is actually what we discussed later. Draw circles of bigger and bigger radius from x naught is going to touch exactly over here, right? Now, have a look at this new. Can I write this analytically? Exactly, right? So this is x naught by norm x0. Which norm? 2 norm, obviously. Why? Because this gives me a unit vector in that direction, and that's exactly what this sphere has radius 1. So this is our projection operation. Is there a compact way of writing this? No, this two cases. Is there a compact way of condensing this? Right. So basically, if I use the max operation, supposing I write this as x naught divided by max of 1 comma does this work? Right. When norm of x naught is greater than 1, I'm outside, then this will give me the unit vector. When I'm inside, 1 is greater than the norm of x naught, it gives me back x naught. This is your first very simple example of a projection operation. This was so simple that we did not have to actually solve any optimization problem, and this is a very useful object in itself. You'll come across this in many examples. Okay. All right, so we are done for today. Anything that you would like me to go over once again? Let's put this into 1:1. So what we did was we started with the brief statement of the PGD, right, and some properties of the projection operation, how to think of it graphically or geometrically, and then we started this proof, right. The proof was trying to get a telescoping series that I could sum, and along the way I got y, and I tried to get rid of y, I got x, and then I used my Jensen's inequality or property of convex sets, and I got that the final expression here, that the average of the iterates is shown to converge. Okay, and that is a weaker version, but there is also a stronger version. Yeah, the tangent cone, the set of all tangents at y is tangent cone. Okay. Anything that I should clarify once again? M some number. I mean, you mean where did it go? This guy, some number, some finite number which is growing slower than k. Then as I take the limit k tends to infinity, f of xk will tend to f star. That's what I want, right? So that is the proof which we have not done, but that proof also exists in the literature. You can find it. No, it doesn't imply. This is not the running average because I started from 0. If you wanted to, you could start from somewhere else. Instead of starting from x0, you can start from x100. It's your choice. Then x100 will appear on the right hand side as well. Right? So it's up to you where you want to start the iteration counter. The form of the expression will be the same, right? Will PGD work for non-convex where the function is itself non-convex or the constraint set is convex? There are two things over here to ask about. So which one are you talking about? See, the function could be non-convex. That's one thing. The constraint could be convex, could be non-convex. So this is it's a good question. How do you define a convex optimization problem when it is a constraint optimization? Both f and the constraint set. So constraint set has to be a convex set and the function, objective function, has to be a convex function. Right? Only when that is the case, this PGD has this nice proof of convergence and so on. Right? But if it is a non-convex optimization problem, then you don't have all of these nice guarantees. Then you have to go case by case and see whether you can make it, whether you can show convergence. There is proof for everything. I haven't done it. Of course, there is proof for everything. All of these statements, as I mentioned, if you had a full semester course on just convexity, you would prove all of these things to gory detail. It's very much possible. I think Stephen Boyd's book, which is titled Convex Optimization, has all of these proofs. Okay. Which statement? It's at the top, right? Second statement. Oh, second slide. Exactly. No, it's remember the tangent is defined as the limiting direction. Not I don't take any zk minus x. I have to take the limiting as k tends to infinity. So yeah, x1 minus y you mean? Yeah, but it's not. I mean, it need not be radially inward, but it's perpendicular to the tangent in this case. I can draw some funny diagram, but at that point where the projection point is, I draw a tangent, and these two lines are perpendicular. I'm stating without proof. Correct. Yes, it is. That's what I'm saying. I'm writing this without proof. It is a true statement. You'll have to take it on faith, and I can refer the proof offline. Okay. Mm. Correct. No, so here it's a slightly different route we have taken. The final term, which is alpha by 2 grad fk squared, there is no, it's a positive term, right? And as long as we said grad fk squared does not grow faster than k, we're fine. It's going to be a bounded sum. So we are not following Zoutendick's proof exactly line by line. So cos theta doesn't show up here. The only thing, I mean, the only reason I reminded you of Zoutendick's condition was because we had used the idea of telescoping series, that's all. Fine?